Hey everyone, it's Dr. Calkins. Today we're going to wrap up week 11 lecture with a little bit more about acids and bases. I think for pH I'm just going to save it for experiment 17, which covers it in detail, pH calculations, that kind of thing. When it comes to acids and bases, we need to know how to recognize who's strong, who's weak, and how many hydrogens do they have. So when we talk about acids, we need to know who is monoprotic. Think about the word. Mono means one, protic means H+. The reason we say protic is H+ is because hydrogen, the element, is number 1, only has 1 proton. And if it's H+, it lost its only electron. Since it has no neutrons, it essentially is 1 proton. To have 1 proton, we're just going to need something that has an equal charge. So all the halogens can do this: HF, HCl, HBr, and HI. These are the ones, and very similar to HCN, these are the ones that end in IDE. So those are the ones that we would have named by the Hydroxic acid. We would have said my ride has Hydroxides, to help you remember that. But notice here we had negatives, so we have positives. And that's what we mean by monoprotic. Other monoprotics that are pretty strong are things like nitric acid and nitrous acid, because those two are negative ones. H is a plus. And we even have one that most students miscategorize, and that's acetic acid. Remember, here's the carboxylic acid group. Here is acetate, -1. Here's hydrogen, +1. These hydrogens do not count. Those are hydrocarbons, those are nonpolar. We also have the larger version. So let's say perchloric acid, chloric acid, chlorous acid, and hypochlorous acid. All of these are negative ones. These are based on the T4-3 ions, just like the nitrates and nitrites were. So those are your list of monoprotics. There's quite a few, but remember, if it has a plus charge, it's going to have a negative match, and if it's 1 for 1, it's monoprotic. One thing we want to look for in this particular idea is who's strong and who's weak. To know who's strong and who's weak, we saw that in the previous lecture. We just need to know who separates completely and who doesn't. I like to learn the ones that do not separate because there's fewer, and that's things like HF. HF sticks together because it's small. So for acid strength, they get stronger as they get bigger. So HF is small, and it's going to be weak. And really the only other one, and you might expect the same thing here, you're going to get stronger as you get bigger. So hypochlorous acid getting close to that, being weak. We just don't see that one too much in Intro Chem. But definitely the one you do see a lot of is this one. Most organics that have carbon are non-electrolytes. This one, because it has carbon, is only electrolyte because it has an acid. Hence the title of one of part of this chapter. But because this hydrogen doesn't get released very often because it's attached to an organic molecule, which is important for the body, but in this case, it's going to make it weak. So even though it's gigantic in size, it is carbon-based, it is weak. So specifically learn HF and acetic acid, both weak. HF because it's the smallest, and acetic acid because it is organic. So let's look at diprotic. So diprotic, very similar in understanding. Di means 2, protic means H+. So here we look for things like H2CO3, carbonic acid, H2SO4, sulfuric acid or battery acid, H2SO3 from sulfite, that's sulfurous acid. Remember, you can say I ate something icky, so carbonate makes carbonic acid. Sulfate, so makes sulfuric acid, so that I ate something icky is a good way to remember those. Down here with sulfite, we'd have Sprite is delicious, so ite is os, H2SO3, and sulfurous acid. Other ones that are fairly common, H2S, that's the fart molecule. So when somebody farts in the car, like your older brother, and rolls up the windows, it burns your eyes, and this is why. H2S is hydrosulfuric acid. So the molecule that were in their butthole is then on your eyeball, and it burns for that reason. So again, same idea, who's weak? The idea of who's weak is very similar to before. Look for those carbon atoms. Just like with acetic acid above, this is weak. Otherwise, if it were strong, carbonic acid that's in soda would eat through the aluminum can, and it doesn't. Carbonic acid is the acid of our bloodstream. It's the buffering system of our bloodstream because carbon dioxide and water can make carbonic acid just like in the atmosphere to make rain acidic. So notice there's not as many diprotic acids, and that's easy for us to remember, more so than monoprotic. So lastly, we're going to do triprotic, and there's even fewer of these. Triprotic, again, tri like a tricycle has 3 wheels. Protic would be H pluses, so look for H3O, H3PO4, phosphoric acid, and H3PO3, phosphorus acid. And unfortunately, these are the big teddy bears, and they're also weak. So they have so many hydrogens, they don't know which ones to get rid of, so they don't get rid of any. They just hang on to them until they're needed by other atoms. So they may look pretty strong in the sense of some labs coming up, or that we've done previously, but compared to others, they are weak, just like those that are organic, and those that are small, like HF. Last thing I want to talk about is hydroxides and how we can look at all of those in one picture in the sense of buffers. Hydroxides are a little bit easier to think about, so as we look at bases, specifically the hydroxide base, just remember that that's based on charge. If you're a group 1 metal, you're going to be a +1 charge. So you're going to expect sodium hydroxide, potassium hydroxide, and so forth. So these would be monohydroxide kinds of bases because they have a negative and these have a positive. No different than if we would go to group 2, that's a +2 charge. So we'd have, say, calcium hydroxide or barium hydroxide. That's 2 is supposed to be outside. So again, they have 2 because that charge of a +2 crossed over. And hydroxide is still a -1 each. So just pay attention to the charge of the family to know how many hydroxides to expect. Oftentimes with bases and with acids and with electrolytes in general, use your solubility table from our week 10 chapter to tell you who's going to be strong and weak. If you're strong, you're a spectator ion. So definitely those sodiums, those potassiums, those nitrates, those acetates were those kind of things, even ammoniums. So if any of those are in some kind of a base situation, obviously acetate would not be, or nitrate would not be, but these in particular, those are going to make relatively strong things, especially sodium and some potassiums. Ammonium hydroxide less so. But again, use your spectator ion list to try to help you recognize strong acids, bases, and electrolytes. If you're weak, it's because you're going to be a precipitate. So you're going to be stuck together most of the time, not separated, not dissociated. So precipitates are a good example of how to recognize weak electrolytes, weak acids and bases in particular. So let's put all this together in one little idea, and then this lecture will be wrapped up. Let's look at buffers. So as we look at buffers, buffers have the ability to maintain pH. pH is just a numerical value for acids and bases. We'll see it in a separate lab, experiment 17 in particular. You'll see it in the PowerPoints. But their job is to maintain pH, so they have to be weak, and that's where it ties into our lecture. So again, they have to stay together most of the time. So it's that 1% of the time that they split up. That's what's so important about these. You can't have a strong acid, strong base be a buffer because they'll separate immediately and have nothing left for when it's important. So as we look at one example, let's just talk about the one that's in our body. We have bicarbonate. Could this be an acid, base, or both? Well, if you have an H, you can be an acid. If you have a negative charge, you can accept more hydrogens that can make you a base. So this is both. If it's an acid, it's going to give its H plus to somebody else, and what's going to form will be carbonate. This is how all those ions tied together back in exam 2. If it was a base and use this negative charge to accept a new hydrogen from somebody else, it becomes H2CO3. So again, it can go both ways. If you look at carbonate though, carbonate is unique that it has a negative 2 but no hydrogen. So this is a base only. It can accept 2 hydrogens, one here and another there. So as it accepts hydrogens in, that's the Bronsted-Lowry definition of a base, it can become hydrogen carbonate or bicarbonate. Because it has no hydrogens, it can't be an acid at all, so it can't lose anything that doesn't have. But notice over here, this would be an acid only, and this is exactly why we call it carbonic acid, is because carbonic acid only has H's. There's no more parking spots. That's an imaginary zero charge. So the only thing it can do is lose H pluses, and that's the definition, in this case, of a weak diprotic acid. So use this idea to help retrace why we changed charges, changed ions back in our other chapter. This is an important idea because this is how Thanksgiving works. A lot of people think that Thanksgiving works because you eat turkey and tryptophan makes you go to sleep, but that's not the case at all. Not everything you read on the internet is true. What actually happens is your body is a buffering system just like this. You eat some turkey, that turkey has to be neutralized. And if you eat way too much turkey, which is typically the case on Thanksgiving or Christmas, and you get tired, it's because your body gets so much food in, there's so much work involved with getting it neutralized, your body doesn't know what to do. Your body's only defense mechanism is to put you to sleep. Because it knows that if you are asleep, you can't eat another piece of cake that it has to deal with in neutralizing its pH. So for the first time all year, you eat all this food with all these different acids and bases like we talked about in our previous chapter. And now, for the first time, you have to be able to neutralize all that in your stomach and your digestive tract, and your body falls asleep. Then it can start neutralizing things by accepting protons from that food to make some acid. It can donate some protons to foods that you ate that were basic and make some base, all in order to maintain your bloodstream's pH to keep your organs functioning properly. This is also how overdoses work. If you inject a bunch of heroin into your veins, heroin's very basic, it's going to kill all these hydrogens. So then, if you're taking this illegal drug or even a prescription drug that's way too basic, all your hydrogens are gone, so now you can't maintain pH anymore. All you have is base left. Now your pH starts to raise from 7.25 to 8.5. You fall asleep, go into a coma, nobody finds you, don't wake up. Same thing happens if you take a whole bottle of aspirin. Aspirin's so acidic that now we take up all of these charges instead. We get shifted over to all acids in our bloodstream, no longer able to maintain pH, and now our pH drops from 7.25, 6.5, we fall asleep, goes much further, we go into a coma, if nobody finds us, we're dead. So I'd like to say that acids and bases aren't important, but it's what keeps us alive. And that's a summary of the rest of this chapter. Catch you next time.